Great, thanks. Hi, everyone. So we're going to part 3. What we've seen before is, what we're trying to do with MCMC is to obtain samples from a target distribution pi. And yesterday we looked a bit at some convergence results that may hold, like either the convergence of the marginal distribution of the chain towards its limiting distribution, pi. And then we may be interested in convergence in total variation or Wasserstein distance. And we may be interested in a rate. So in the very simple case of the donkey walk, we identify the convergence rate using a coupling argument. What did we do? So we talked about the central limit theorem, which we can prove using the Poisson equation from a central limit theorem on martingale different sequences. And so today and tomorrow, we're going to go to less theoretical, more methodological considerations. And just to clarify, so if you go on arXiv, you look at the recent preprints that concern Markov chain Monte Carlo. So first you'll see that there's a lot. Practically every day there's at least one paper on Markov chain Monte Carlo, usually in the stats section of arXiv, but sometimes in probability or physics or across different branches. And I would say 90% of those contributions would be either proposing a new algorithm. These are very general, but often more like tailor-made to a specific type of problem, like a new MCMC algorithm to sample this distribution that arise in this setting, or theoretical results, so convergence results, for example, for classes of problems like Langevin Monte Carlo, Hamiltonian Monte Carlo on log concave target distributions in a certain metric and so on. So that, I would say, is most of the research on Markov chain Monte Carlo. But what I'm going to talk about today and tomorrow concerns a bit of a different, it concerns a different aim, which is to say that in this game, you have already your MCMC algorithm. It's obtained before, it's given to you, or you just designed it, but it's there now. So you have a transition kernel. Corresponds to your MCMC algorithm. So let's say that you did the best job possible to obtain a good one in some sense. And now we're going to be concerned about how to best use it. Right? So the very canonical way of using it is to run t-steps of this algorithm. Oops. And then to compute an ergodic average. So an average over the trajectory of the chain, perhaps after discarding the initial portion of the chain that looks like it was a transient. But it turns out for the same Markov kernel, there are other ways of using it, either to obtain a different type of estimate, not this one, some others. So we're going to look at unbiased estimators, for example, as an alternative to this, or to get perfect samples, exact samples from pi in certain cases. So today we'll talk about a technique called coupling from the past that achieves that, or to obtain practical convergence diagnostics. So we can do a theoretical study that may tell us something about the rate of convergence, but usually in practice, even the best study still leaves you with a rate that is partly intractable. It contains constant that you don't know how to evaluate for your particular problem. And so it turns out maybe in some cases, and using couplings, as we will see, we can obtain more concrete views on how the algorithm performs. Okay. So of course, if it turns out that this Markov chain Monte Carlo algorithm is actually not very good for the problem at hand, then whatever you're doing with it, there's not going to be any miracle. Right? So we assume here that it's given, hopefully it's good enough. We're trying actually to assess whether it's good or not. But if it's terrible, then everything is going to fail. Okay. Just also to point to a nice interactive website, gallery, where you can see different MCMC algorithms in action. There's the link in the first set of slides. So if I zoom in. So here you see that there is the contour of a two-dimensional distribution. And an algorithm was selected. So here it's called Gibbs sampling. There's a target distribution, which is called banana here, because it's kind of looking like a banana. And what you can see moving around is the point of the Markov chain. So the Markov chain has already produced those gray dots. I don't know if you can see them at all. There are some points at which it was going, and now it's currently moving around here. So you see this Gibbs sampling. So it's moved on the other side now. Gibbs sampling here refers to the idea of moving only the X component, fixing Y. So that is a horizontal move. Or moving only the Y component, fixing X. So that's a vertical move. So the chain is doing only one-dimensional updates. So it's simpler, but on the other hand, it's, for example, if you want to walk diagonally and you're only allowed to do horizontal or vertical steps, it's going to take a lot of steps. And so here in that website, you can play with, if you type MCMC interactive gallery, you'll find it easily. And there's a bunch of algorithms here, so we can recognize Hamiltonian MC, Monte Carlo. Mala refers to Metropolis adjusted Langevin, and there's all sorts of other crazy stuff. So if we do Hamiltonian Monte Carlo, get those nice trajectories. So at every step, we solve the Hamiltonian dynamics, and then we retain one of the points to start the next step. And every time the velocity, the initial velocity is refreshed from a multivariate Gaussian. And so you can accelerate things also to get lots of points. Where is it now? It's gone. It's going back. Okay. And so slowly you see that there are histograms that are getting populated for the two marginals. And eventually they will converge to the marginal distribution of the target. Okay, you can change the target. It's quite well done. Here's a case where you have multiple modes. So the chain is currently stuck in the top right mode. Maybe at some point it's going to manage to escape. But it could take a while and so on. Okay. So of course that's only possible in two-dimensional continuous spaces, but MCMC sometimes is used in sampling on the space of partitions, for example. All sorts of complicated discrete or combinatorial spaces for which visualization itself is a challenge. Okay. Okay, so let's get started with coupling from the past today. So it's going to be very toy, very, in a sense, a self-contained few slides on this ID proposed by Prop and Wilson, a paper called Exact Sampling with Coupled Markov Chains, Applications to Statistical Mechanics. That was really a big, huge deal when it appeared in the literature in the 1996. And I must say then afterwards people tried to apply this to all sorts of problems and mostly it didn't work. And so this method is not so well known, but conceptually, and in some cases it works even though some cases are challenging and yet it works. But unfortunately it's not generally applicable. And so even in, for example, the probit regression example that we talked about, we don't know how to use coupling from the past. Okay, so here we're going to look at a very toy example, finite state space Markov chain. So the state space is just, say, 1 to little n. There are n states. There's a target distribution pi on there. And we have a Markov chain that goes from state to state. So typically, Markov chains on finite state space are represented by diagrams where you see the different states. And you have arrows describing the probabilities from transitioning to some states, to some other states. So maybe there's probability P1, 2 to go from 1 to 2. Maybe from 2 you can go back to 1. Maybe from 2 you can also stay in state 2. Maybe from 1 you can go to state 3. And from state 3 you can only go back to state 2, for example. So all those probabilities, you can put them in a matrix of size n times n, describing the transition probabilities from states to states. Actually, so it's quite nice in discrete state spaces because you can work with matrices and, for example, the target distribution, the invariant distribution will be an eigenvector of the matrix corresponding to eigenvalue equals to 1. So you have lots of nice properties which we haven't talked about, but if you look at the lecture notes of Levin and Perez on Markov chains, there's a lot of very nice content specifically for the discrete case. Okay, so here we're going to say that the Markov chain evolves by application of random functions. So that's here denoted by xt, the chain at step t, is obtained by drawing a random variable. We can think of it as a uniform, or maybe a bunch of uniforms. And then deterministically, once we have the uniforms and the previous states, we can do some calculations and obtain the new state. That's what it means. So here, psi is a deterministic function that takes as an input some fresh randomness at every time. Okay. But we can also look at it as the application of a random function, which is the function that maps x to psi x comma u for a random u. And so, of course, it's an iterative procedure. So if we apply psi t to xt minus 1, but xt minus 1 was obtained from xt minus 2, and so on and so forth. So we see that this is a composition of t random functions, starting from some x0, that we will think of it as an arbitrary initial state. Maybe it's drawn uniformly among the n states, for example, or it's just deterministically one of them. Okay, and so the first trick that we're going to do, you're going to see it can be a bit puzzling, and it's a bunch of tricks. Nothing is complicated. At no point I will call for a very serious result in probability theory, but yet I think the result is a bit puzzling. So the first trick is that xt, obtained in this way, in the standard way, going forward in time, has the same marginal distribution as if you compose those random functions in any order, in particular in the reverse order. Why is that? It's because the randomness of this function at time t is refreshed independently at all times. So the distribution of psi 1 or psi 2 or psi 3 they're all the same. They're all independent from one another. So you can compose them in any order. The label 1, 2, 3 or t minus 1, t minus 2 are irrelevant here, okay? So that means that if you were to compose the same function but in the reverse order, you would obtain a variable yt that has the same distribution exactly as xt. Okay? But it's not the same function, okay, still. It's not the same sequence in particular. Okay. So just to be clear, so if you look at xt, yes?
Sorry, so my standard understanding of like what we're doing with like more basic Markov chains is we're applying a transition matrix over and over again, and it feels like this has the same flavor, but we're allowing the function to be different at each time step. Is that sort of what you're thinking about?
No, it's the same. So it's the same. So, but what you mean by applying the same transition matrix is actually in practice, so you're at xt minus 1. It identifies a row in that transition matrix. But then you have to sample one of the states according to the probabilities given in that row. Yeah? So for that, you need a uniform or something like that. It's a categorical distribution that you're drawing. And so that requires some random input. And so in that case, the random input is ut. And psi is the function that selects the right row using st minus 1 and then selects the right state according to the draw of ut.
Thank you.
Yeah.
So should we keep that in mind as an example when we look at your psi function?
Yes. Yeah. But with the little nuance we'll go back to, which is that for the same transition matrix, so the same Markov chain, there may be multiple psi functions that achieve the same law.
And so the psi, let's say I wanted the both psi 1s and the bottom, does it have its own u1 element?
Yeah, each of the psi has. The thing, I would have written everything there, but you can imagine the nastiness of the expression I would get, because it would be phi of, phi of, phi of, phi of, da 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 da, and then comma, ut, comma, parentheses, comma, ut minus 1, parentheses, comma. So it's nicer to write it with a random function.
Fixing the psi is that the u I draw to define psi 1 is the same on the first and the second display?
Yes, exactly. You can think of it that every trajectory of the chain corresponds to an infinite sequence of u's. Okay, and if I draw that once and for all, the infinite sequence of u's, then I can apply my functions in different orders, and I get different values. That's important to understand because, in particular, so if you do one more step in the forward chain, xt, so you were at xt, you do one more step, so you can go in different places, according to psi t plus 1. But in yt, if you do one more step, that means that you're going to apply the same function as before, but instead of applying to x0, now you're applying it to psi t plus 1 of x0. Okay? And it's going to be quite different. Yes?
Sorry, this goes back to what you mentioned before about like MCMC can be applied to groups of like partitions, like space of partitions of individuals. I'm just curious how that's like applied there. Could you please elaborate more? Like with the like when we have a population of individuals and we're studying like the partition or like the grouping of individuals.
Yeah, so I'm just thinking of discrete examples, discrete state spaces. And for example, on the partition, if you want to sample uniformly in the space of partition, you don't need to do MCMC. You can do it exactly. But if you want to sample non-uniformly, for example, there are distributions that are basically putting mass on different partitions according to some weights. Then it may not be so obvious to exactly sample from those distributions. But you can do it with MCMC. Meaning you start from any partition, and then you propose a modification of the partition, for example, by swapping to assignment of the partition, so two indices, if you like, and then accepting or not this new partition according to the target ratios. So you can do a metropolis type algorithm for partitions. Why would you want to do that is another story, but if you look at distribution of weighted partitions, you'll find some use of that. I won't go into that detail. Yeah.
Just from understanding, to connect it to what we were studying yesterday, if we were to have defined yt to be the same sequence of functions as xt, so we have a phi t, or psi t equals with psi t minus 1 all the way to psi 1 evaluated at x0. Comparing that to the common random numbers approach, we're applying the same sort of functions. If we were to not just apply the same random functions, but the same realizations, is that common random numbers?
Yeah.
Okay.
That would be called common random numbers, yes.
So this is the difference between common random numbers and here is that yt, the u's that go into, like the actual realizations that would generate the samples of yt could be different? Is that correct?
It's kind of, so here, for a given realization of the U sequence, I'm thinking that then this psi1 in the X chain would be the same realization as the psi1 in the Y chain. But it's not applied in the same place.
So if we were to have swapped the order as written here so that the order of the size in the xt display and the order of the size in the yt display, that is common random numbers?
Yeah, it's common random numbers and reverse order.
And reverse order? I don't think I see that part.
So it is the same psi that I'm going to use for the X and Y. In fact, we'll see, we'll focus on the Y in the next slide. Can we go back to your question? Yeah. Thanks. Okay. So just to imagine what it looks like with 5 states. Okay. So we have 5 different states. Those arrows describe the realization of those random functions. Okay, so the random function, and it's weird because I'm starting from a negative time now also. But forget about that for the minute. Say, from state 1, depending on the transition probabilities in the matrix, maybe you can go anywhere. Maybe you can only go to state 3, I don't know. But once you apply the U function, once you realize the associated randomness, you will go from 1 to a certain state. Okay? So that's your categorical draw, if you want, corresponding to the row of the matrix. And if you start from 2, here you go to 3 as well. You start from 3, you go to 2. If you start from 4, you go to -2, 1, sorry. If you start from 5, you go to 3. Okay? And then if you draw a new function that gives you those arrows now, so now from 5, you would go to 3. But if you started originally from 5, in the first step you went to 3, and so now after the second step you go to 2. Okay. Does it make sense what this represents? So I've realized all of my uniforms, and now I have a set of arrows, and if I want to trace the trajectory of the chain, I follow the arrows. Okay. Start from an arbitrary initial point, I follow the arrows, that gives me my trajectory. Okay?
The first set of arrows is the definition of phi 4.
Yeah, that would be, say, phi minus 3 in the previous notation, but a particular realization of it. If I redraw the u minus 3, I would get maybe different arrows. Sometimes you will not get different arrows because, for example, if from state 3 you can only go to state 2, and every time you're at state 3, you deterministically go to state 2, so there's no randomness there. Yeah.
Is the same use across 5 chains at every time point?
So one u determines the function psi t. And so that, it's a function, so it's not just one arrow, it's a set of arrows. The function gives you how you go from the state space to the state space.
And this function is the same across all 5 Markov chains in this graph.
Yeah, I'm thinking more that there's one Markov chain, but there's 5 different states that it could be in, and so it would transition to a certain number of states in one step. But one trajectory would only go to one state in each step, of course. Okay. So if you go now and look at the backward process, so what does it mean? It means suppose that you want to do, if you look at the forward process and you want to do one more step, it's happening here on the right-hand side, right? So you were either in a 5 or 4 after all of this, but then at the next step you may be anywhere depending on the new arrows that you would draw. But if you look at the backward process and you do one more step, it would happen on the left-hand side, okay? And now let's look at what happens already there, right? So from 5, if I follow the arrows, I get to here, 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 and I end up in 4. From 4, I follow the arrows, I end up also in 4. From 3, follow the arrows, I end up in 5, I think. From 2, I end up in 4. And from 1, I end up in 4. So whatever you do when you add arrows on the left, you already know that you're going to end up in 5 or 4. You go arrive at any of those 5 states, but after that, for sure, you end up in 5 and 4. Okay? So now you can imagine doing that many, many times on the left instead of on the right. What may happen is that the process could coalesce, meaning that there may be a time when, as you continue to recurse backward, no matter where you start, you arrive exactly, say, in 5 or in 4. Okay? And from that time onward, you could add as many steps to the left, but you know that eventually you end up at time 0 exactly at the same state. So you don't have to, if you want to know where you're going to arrive after t steps, at some point you can stop. Right, so there's a time t star, call it the coalescence time, from which wherever you started, after t star steps backward, you end up always in the same yt star. It's not at all the same as if you look at the forward process where you expect to keep moving around according to the transition probabilities. So if you look at the backward process, there's a point at which you can continue backward recursing, but you would arrive exactly at the same realization. And so for all times after that, it's the same. Yt star corresponds to where you would go for any t after that, so it's the limit. Okay? So in a sense, the trajectory of yt at some point becomes completely flat. You confused already a bit?
Yeah. So I feel like it feels similar to a periodic Markov chain, right? Which is like if you go back to the thing, it's like every 5 steps I visit the substates, which is 4 and 5, and then even from there, you know, assuming
Right.
I have like 1 and 3 will only point to 2, and then 2 points back to 1 and 3 with some probability. Like, it feels in the spirit of that to me, but I guess I'm confused by that idea of limit, right? Because, okay, I can run the chain infinitely backwards, and eventually I'm going to get to 4 or 5, but that doesn't mean that I stay in 4 or 5, right? Going forward.
Going forward, no. But going backward, yes. In the sense that, as we said, like, if you at some point have to go through those states, and those arrows are fixed, whatever was the path that led you to those 5 states, now for sure you're going to end up in 4 or 5. You see? But that's really because we fixed the arrows now. If you were to redraw the arrows, you may end up somewhere else. Yeah.
Am I right that drawing the arrows is the same as drawing the U's?
Yeah, drawing the arrows is the same as drawing the U's. Yeah. Like if you realize the function, a function in this, in finite spaces is just a way of mapping the 5 states to 5 states. Yeah.
Once the U's are drawn, they're realized, I can think of them as the parameters of these transition size, right? So it doesn't matter how I put you the order, they're always going to be the same transition function.
Yeah, exactly.
And if I would go back and look at 5 periods earlier, so the transition that happened in those 5 periods would correspond to 5 other U's.
Yes, exactly.
It doesn't matter what it looks like, as long as later on it goes through this
Exactly.
period.
Yeah. Like the new randomness is going to just determine where you're going to end up at this time. But from that time, we know already exactly where you're going to end up at time 0. Yeah.
As the number of state increases, you can guess that the coalescence time is going to be larger.
Oh yeah, that's yeah, of course. You'll see an example where it still works in a very large dimensional or large cardinality set somehow. But yeah, it's expected to be more and more. The coalescence time probably depends on the number of states. Yes.
And so if the space space is continuous, could be that coalescence time is
Yes. Yeah, you need some additional tricks to handle anything in the continuous case, which I'm not going to really talk about. But it's already, I think, confusing enough in the finite state space case. So, okay. Okay, so we've seen that maybe at some point it's going to be coalescence, and then you can recurse backward as much as you want, but you know that at time 0 in the previous graph, you had exactly this location, yt star. But we say that for any time t, the law of xt was the same as the law of yt, because applying the function in any order in terms of the distribution that it incurs makes no difference. And we know also, well, that in the MCMC setting, we assume that we constructed the chain in such a way that the limit is the distribution that we're interested in, the limit of the forward chain. Right? But now we actually have everything to conclude that yt star, which corresponds to the limiting value of the yt process, must be distributed as pi. Okay? Because in a sense, we are touching the infinite backward in a finite time from the guarantee that if we did any more steps, we would not change the value that we would get. So we might as well stop, or we might as well consider this to be a limiting value. The distribution of the limiting value from this, right? If the limit of the law of xt is pi, then the limit of the law of yt is pi as well, because it's the same law.
Can we think of xt and yt as independent draws on the same distribution? Since they have the same marginal, even though they start from the same place. So that when I permute all these different transition size, I get a full sample.
So the idea later will be to just do that many, many times independently, but not to compare xt and yt. The idea would be now we know how to sample from pi, so we get yt star, and we do that many times independently. We're not going to compare the distribution of xt and yt, apart to say here that it's the same marginal distribution.
So this is conditional on all the use that you know.
I know the equality in law is not conditional on the use. In fact, the only randomness is coming from the use. So the law of xt means the law of composing t times this random function. And the law of yt is also the law of composing t times those random functions. And we're just using the fact that the composition has the same law irrespective of the order. And that's because we refresh the u independently across times. So psi1 and psi2 are distributed in the same way. Yeah?
Just to clarify, so I understand from the picture before, if you eventually withdraw arrows that all go to, let's say, 5, wherever we start, so we must end up at 5, so like the chain coalesce, and I have different coalesce in that line. But why is that? Why is it formalized by the text on the top of the next line?
So coalescing means that wherever you would start, after a certain number of steps, you arrive at one and only one location.
Yeah.
So you could say that, so that's what it's formalizing. For any starting point, you're always at the same value. You could say that it means the cardinality of this, of the map of the whole state by this function now is equal to 1. That's the coalescence time. You can also see maybe intuitively why it would happen eventually, because as you recurse backward, you're only decreasing the number of possible value you can end up. But for example, here at this point, there's 5 states, but only state 3 arrive in 5. The other states arrive in 4. So now if the previous arrows don't arrive at 3, we're losing state 5. Okay? So eventually we're losing state one by one until there's only one left. Yeah?
This might be silly. Like, so if I just run it for long enough, does that necessarily mean that it will like always sort of converge into one point? Like,
Is it guaranteed that there would be coalescence?
yeah. Like, isn't that like actually part of the problem?
So it's not guaranteed. There are, of course, conditions. So for example, if your Markov chain goes, I mean, maybe that's relating to the periodicity comment. If it always goes from 1 to 2 to 1 to 2, so deterministically, it's still a Markov chain. And then, of course, the arrows go up and down and up and down. And then, what happens? So that means if you start at 1 or 2, it deterministically decides whether you arrive t steps later, but it's not coalescing. Even if you do a less trivial case, so that's going to be maybe a bit subtle, but if you imagine that you have only 2 states, and what the chain does, it stays where it is with probability p, whether it's in 1 or 2. Otherwise, it's transitioning from one state to the other, so with probability 1 minus p. Okay? So for that particular chain, so that defines exactly a transition matrix. Huh? So this one, so that's P. But there are multiple representations in terms of random functions corresponding to the same transition, some of which will lead to coalescence, and some of which will not. So for example, if what you're doing is, so with probability P, so you draw a uniform, you compare it to P, and you stay where you are if the uniform is less than P. So then if the states are, if the 2 chains were different, they will remain different. And then with probability 1 minus P, you decide to swap. But then if 2 chains were different, they will continue to be different. Right? So you'll never have coalescence. So that corresponds to psi of x u equal, so x indicator u is less than p, and then the swap x, so if I'm calling them 1 and 2, I guess it's 1 and 0 would be easier. Huh? So I would call it the other x, you know. Is it 2 minus 1 absolute value, perhaps, or 2 minus x, well, whatever. You see what I mean, like indicator that u is more than p. So that particular random function representation does not lead to coalescence, but there is another one that leads to coalescence. Yeah, it's couplings. Yeah, it's called coupling from the past. Yeah, for sure. Yes, yeah, so what would it be? The random function corresponding to the same matrix that would possibly lead to coalescence. Any idea? Maybe to make things a bit simpler, we may assume that we're in the case where P is, say, less than 0.5. And then we can deal with the other case or not. It's not easy. The goal is to find another type of function, also that depends on the current state and U. And U could be one uniform, but if you want to have two uniforms, you're allowed to have two uniforms. It's a source of randomness for one step. Such that the distribution of this, when x is fixed, is given by either P 1 minus P or 1 minus PP, depending on x. Corresponds to the transition matrix. Any guess? Yeah.
So could you just have two uniforms, basically one corresponding to each row?
Yeah.
That are independent?
Yeah.
And that way you get, you get both the cross arrows and the straight arrows.
Yes. But,
Each,
so
if they're independent.
basically, in order to have coalescence, you need indeed, in terms of the arrows, that sometimes this happens, or sometimes this happens. So you're trying to engineer a function so that this could happen. Yeah.
So just to clarify, like, I guess if you can have two uniforms, you can sort of induce that, like, is the idea that maybe I want to consider, like, all possible permutations of things that can happen, so maybe in state one, I want to imagine the two probabilities of moving to the next state versus in state two.
Yeah, I think that's
like kind of complete contingent plan, and then I
yeah.
just partition U that way, and with the correct probabilities. Is that kind of
That's pretty much it. So one way of looking at it is, you're going to end up in 1 or 2 with probability P, 1 minus P. So here it's bigger because P is less than 0.5. So that's the look at the conditional distribution if you are currently at 1. But if you are currently at 2, it's like this instead. Right? You agree? But you see that the pointwise minimum is not 0. So from whether you are in 1 or in 2, there should be a chance of being in 1. Okay? But that's not happening with this particular choice of function. So it doesn't have to be like that, but it could happen. So for example, you could say that, so psi of x, I think I'm going to use 2 u's for that. So I'm going to put it on 1. So it's going to be 1 if, say, u1 is less than p. In general, you could say less than the minimum between p and 1 minus p, but here I've restricted the case. Okay, and then for 2, so in the other case, he must be going to 2, but in what probability is going to happen? So that depends on where x is at the moment. So you could say indicator that x is in 1. So if x is in 1, it should go to 2 with probability 1 minus p. So maybe I'm going to put an indicator. Maybe that's overly complicated. I know, because I already have the chance of going to 1. I know, so I need to be only in that case. I know, yeah. Actually, I'm confused myself now. I mean, it would be easier to first write it maybe in terms of the different cases, and then write in terms of indicators if that's convenient for the code. But we could say, so say if x equal 1, we're going to put 1 if u is less than p. But if x equal 2, what do we do? So we want to be potentially also going to 1 in that same event. But otherwise, we still want to go to 1 sometimes because there's a gap between p and 1 minus p. So otherwise, if u2, so we're missing 1 minus p in that story, right? The gap here is 1 minus 2p. Okay? To follow what I'm trying to do? Trying to engineer a function such that I could end up in state 1 with some probability whether I start from state 1 or 2. So I'm going to say that this should happen with probability 1 minus 2p. And otherwise, I'm in 2. So now we need to check that indeed we are in state 2 with the right probability. Yeah. That would work? Yeah, it could be that it would work, yeah. Okay, so it's just a very more complicated function. Hopefully we can work it out. Such that, I did work it out this morning at 7 a.m. and I obviously forgot already. it's a bit confusing, but we should be able to work it out. Okay, so there could be coalescence or not, indeed. It's not guaranteed, but it could be that there is coalescence, and if there is coalescence, then the point that we obtain at the coalescence is a draw from pi. So the algorithm would look like this. So you start with the composition at time 0 is the identity, and then you repeatedly go back in time. You draw the arrows. So that's the arrows, the psi-t function. You compose. So your new composition is obtained by composing the previous composition with the new arrows. So that's adding arrows on the left of the diagram. And you do that until the composition maps the whole state space to just one value. So the cardinality of the mapped state is 1. And whatever that unique element is in there, that's your draw. And the coalescence time is the step at which this occurs. Okay? It's kind of a conceptual algorithm because it'd be very cumbersome to implement with large n and so on, but yeah.
So I think I'm a little confused on how the fact that we're talking from the past, like that from the past part, I feel like if I were to change everything instead of t minus 1, if I had t plus 1, and if I were to do things in the forward direction,
Right.
I'm confused on how the actual knowing the u's and knowing, working backwards is actually operating here.
So if you were going forward, you could have coalescence as well, right? Because it's the same arrows, right? So if you go forward, at some point, there will be the coalescence. So wherever you start at time 0, at some point in the future, you're necessarily just in one place. Okay? But the problem is, we can see that this cannot be, the location of that unique coalescence point cannot be distributed from pi. And I'm going to show you why. If you have, say, a Markov chain that goes to a certain state only from another state, okay? So here you have maybe this situation. So you can only go to 3 from 2. So if you look at the coalescence forward, okay, where could it be? And it cannot be, at the time of coalescence, it cannot be at 3. Because if it was at 3, that means you would have already been coalescing at 2 before. Right? So it cannot be the first time at 3. And so if you were to coalesce forward, there are some states that you could never reach, but they could have some mass under pi. Okay? Somehow this doesn't happen in the backward process. Because you could have arrows that point to 2 and 1, and then you do one more step backward, and now the arrows only go to 2. And from 2, maybe there's some further arrows going to 3. But coalescence occurs because now you're losing the path to 1. That's happening only in the backward sense.
So if I wanted to study this, but going backwards,
Yeah.
would the right way to do that be to redraw this graph, but change the direction of the arrows that we've drawn on the board? And would that be the way to see if we have this problem drawn in this way looking forward? If we were to see that OB coalesce at 3, it must have been OB coalesce at 2. That's what you.
So first, I discourage, it's already confusing to start from negative times, but I discourage inverting the direction of the arrows. In my experience, it's not going to, it's going to make you think about the, so a pi invariant Markov chain also has a backward transition kernel, which is not the same as its forward transition kernel, but this is not what this is about. Yeah. So you don't want to be thinking about the distribution of xt minus 1 given xt in the Markov chain originally defined as with xt given xt minus 1.
I think I was conflating the two, so those are different things.
Those are different. Yeah, here's this backward process. In a sense, it's... let me give you another example that may be helpful in continuous spaces. Okay. You're familiar maybe with the autoregressive process of order 1. Okay, so where yt is, let me keep using xt for the forward process. It's say rho xt minus 1 plus some Gaussian noise. Okay, so if you go forward in time, you could say that this is the same as rho square xt minus 2 plus rho epsilon t minus 1 plus epsilon t. So here I'm doing the decomposition that is forward, right? So if I do it many times, I think I would end up with rho t x0, and then you have a sum of rho to the power k, epsilon t minus k, maybe minus 1 here, k equal, k equals 0 to t. No. I need to k that starts from 1, but I'm putting minus 1 here. More or less, okay?
Well, I think you were right. You need the epsilon t.
Yeah, I need the epsilon t.
You need the epsilon t. You started at 1 with the epsilon t.
Yes, yeah, that's fine. Yeah. Okay, I'm terrible at this. So what's happening? So when you go forward, what's going to happen? This would go to 0 typically, right? Rho is, let's say, in the stationary case, rho is less than 1 in absolute value. This goes to 0. And this you can see every time you're discounting the previous sort of accumulated noise, but you're adding a new noise. So the process keeps moving around. It looks like a minus. But if you do it backward, it's a very different story. The trajectories look nothing like those trajectories. Because what would it mean? It would mean that, so the function psi of x here, let's say that epsilon t is directly the source of randomness. So that's the function that maps these to rho x plus epsilon t. Okay? So what happens when you're composing backward is that you're replacing the argument of the composition by one more step, the psi t plus 1, right? So you'd be replacing this. So in other words, in the backward process, what happens? So the first step looks the same, right? So, but let me go back to my definition here. Yt, it's y1, so it's rho of, and then rho of, and then rho of x0 times x0. But I'm adding the latest noise here in the middle, in the part that's pre-multiplied by rho to the power t or t minus 1. Then I'm adding a more recent noise. Da-da-da. And at the end, I have the latest, the only noise that's not multiplied by some power of rho is the very first one. Okay? So once it's fixed and I'm doing more and more iteration, so when t goes to infinity, I'm just adding stuff here in the part that's multiplied by a very, very small number, rho to the power t. Okay? And so if you look at the trajectory of that, basically the steps are smaller and smaller. And so the trajectory of that Yt process looks like this. It's converging to a fixed value. But if you take any particular fixed time, Yt has the same law as xt after the same number of steps. So that means that if you were to refresh all the epsilons, you may obtain a very different y at that time. But on the other hand, doing more steps will not give you a very different value. But so in the continuous case, it doesn't ever coalesce exactly. It just gets... if you try many different starting points here, they would all go to nearly the same value. I mean, they would coalesce, but they would not exactly be the same value, ever. But the same principle applies. Yeah.
So if it's the case that going this backward process, we have this epsilon 1 all the way to n, where we converge to as t goes to infinity, is that epsilon 1?
No, it's still like it's a convergence series, but not equal to 0. So it's equal to some value. In fact, if you were to do it many, many times, yeah, you would obtain a draw from pi, the invariant distribution of the AR1. Okay. Actually, probably you can work out that the... I mean, maybe it's simpler to say x0 equal to 0. We don't have this bit. And then what would happen here, you'd have, I feel like you would have something like, you'd have something like if x0 equal to 0, here you'd have the sum of rho to the k, epsilon to the k, I think, something like that. Huh? Well, you know, the new, or up to t. So the new guys are squashed in that story. So that doesn't converge to, that converges to a certain value that would depend on the realizations of the epsilons.
So when they coalesce is a story where we've drawn all the 5 functions, and then regardless of whether randomly pick the first observation, we need that
Yeah.
exact value of this.
So at some point,
But then we want to talk about Yt stars and
yeah, Yt star is random because the realization tell us where the coalescence occurs, and that's Yt star.
and then here can we see why coalescing forward does not imply that we're at a stationary distribution?
Well, there's no coalescence really here, so it's complicated. If you have to go to infinity, then you indeed get a draw from the stationary distribution. But what's nice in the coalescence story is that your algorithm terminates in finite time.
No, just trying to understand why when you answer the part, you say they're going forward because draws.
Yeah, no, my only argument for that is the fact that you can't, in the forward coalescence story, you can never, this algorithm would never output a point that has only one antecedent. Because it would have to have coalesced at that antecedent in order for this to spit out that point. And so by definition, at the coalescence time, you would have outputted another value. That's my only intuitive explanation for that. So, not very intuitive. Okay. So it remains to see that indeed the coalescence time is finite. And again, with that story of simply two states, we could see that even for the same chain, it really depends on the choice of random functions that you're using. It could coalesce or not. And so you could show that if there is irreducibility, so if you can go from anywhere to anywhere in a certain number of steps, then there exists, you can construct a random function representation of the chain that leads to coalescence. It's just a bit of the same argument as what I've done. So before you have the states, and after k steps, there's at least a minimal probability of being in any of the states from any state. Okay? Because the state space is finite, so you take a minimum of all states. And so there is a random representation where you draw a little uniform and you're in one with that probability. And so you would coalesce there. So that really exists if you have irreducibility. But not necessarily the one you're using for convenience, but there should be one. And then it would occur with a geometric rate, actually. Because if in k steps it has a little chance to occur, the waiting time for the success is like a geometric random variable. The time it takes for a Bernoulli flip to be equal to 1. So it could be with an extremely low rate, but it's a geometric rate. Okay. So, yeah?
Maybe this isn't helpful, but is that sort of like a concrete rate? Or is that kind of like I take the worst possible?
Yeah, it's a worst possible thing. Okay, so is it useful for anything? So actually the paper of Popp and Wilson was really a big splash because they sampled a realization of the Ising model, on the state of cardinality 2 to the power 4200 times 4200. So it's the space of Ising grids. So the model is as follows. The Markov chain has a state which is a grid, and at every location in the grid, there's a so-called spin equal to -1 or +1. So here you have a little xi equal to -1 +1. And there's a grid of those, and they looked at a grid of size 4200 times 4200. Large grid. Every spin can be any two possibilities, so the cardinality is massive, 2 to the power millions. What's the model? So the model is pi of x, so the whole grid has probability proportional to exponential times beta, a real value, times the sum of all neighbors in the grid. So you can say that, for example, each spin has four neighbors, of the product of the spins. So that means you get a positive value if two nearby spins have the same color. Right? So here they are black and white, corresponds to -1 +1. And so if beta is positive, that means that the grid, the image that you're looking at, should be such that nearby points have the same color. So that's why you see pattern. It's not like white noise completely, like there are some sort of stains of sort of the same color. So the goal is to sample those x's. And the way that the algorithm worked, this MCMC algorithm that was employed, is the very naive, actually no, to reach that scale they use a not naive at all algorithm, but coupling from the past could work with a very naive algorithm where you're doing deep sampling. Basically, you're updating just one of the spin, conditioning on everything else. And so there's only two possibilities for that spin, so you can compute the probabilities. It only depends on the neighbor, so it's a quick calculation. And you draw a Bernoulli flip for every spin. You do whole sweeps to update all the spins. And so, it would be completely hopeless to do exhaustive searches on the whole state space here. So you cannot follow the arrows from all the points in the state space, all the grids. It's impossible. But they show that actually it's enough to control only 2 states, in the sense the so-called extremal states. So say only the first one and the 5th one here. Because the updates that they use, the random functions that they use, guarantee that there will be no crossing of the arrows. And so if the smallest and the largest states coalesce, automatically they know that if the chain had started from anything else, it would have coalesced maybe before, but by then. Okay, so that allows them to only to have an algorithm that's practical, where they have only 2 grids that they update using the same random numbers. And when the 2 grids are the same, that's when they output the grid. And so they reached that, and people were like really amazed, because there had been at this point already 30 years of MCMC for this problem, and no one had seen a real draw from the Ising model. Of course, it looks exactly like an MCMC draw from an Ising model, but this one is real. Okay, this is perfectly distributed according to pi. It's not visible, of course. It's just one realization. So, but that was a big, that was not an easy problem given the large cardinality. And as I said, they sample. They managed to do coupling from the past from a basic Markov chain, but a less basic as well for this problem. And so there was a lot of hope that this would then be applied to all sorts of complicated scenarios. But in fact, it has some successes, but I probably imagine most of you haven't heard of it. So for example, that maybe say something about its relevance in econometrics and statistics. But there are interesting developments. So there's a book by Mark Huber called Perfect Sampling, from a few years ago, that describes the various developments. Any comments on that? And we'll move on to something else afterwards.
You need case-by-case cleverness to find the function. And then on top of that, in terms of getting involved, they need to be like even more clever to find a kind of bound.
Yeah.
They have a lot of homework if you want to do this software program.
Yeah.
Like if you want a bound direction, especially if you have an idea for a bound, for a coupling that gives you a non-isolating mixing bound, is it clear that you can recycle it into a function?
No. No, because the existence of those extremal states, they're very simple. In the case of the Ising model, it's the image that would be completely black and the image that would be completely white. You start from that. It's very specific to this problem. Like if you have regression parameters.
But for a given problem for which I have a coupling that gives me a non-isolating mixing bound, do I have a strong start to getting...
You have maybe an ingredient.
Okay.
Yeah, maybe it's better than nothing. Yeah. Actually, when I worked on these things that I'm going to present, when I worked on them, so I spent one day thinking that I had solved the perfect sampling problem. It was one of my best days. So I woke up one morning and I was like, I was working on the stuff that I'm going to present next, but one morning I was like, but this is it? This is perfect sampling? And I spent the whole day smiling. Like my cheeks were hurting at the end of the day when I realized the mistake that I made. And so now I appreciate there's a big gap between just coupling stuff, which are great and useful and exciting, but perfect sampling is kind of the holy grail for the Monte Carlo aficionado. Omkar?
I was going to ask, we found an example of a transition probability kernel that has different choices of these random functions. One of those choices did not have a coalescence time.
That's right.
The other one did.
Yes.
And I'm wondering, is there anything to be said about, given these different choices of these functions, can anything be said about like the structure of them leading to faster coalescence times than others, or maybe like what is the smallest coalescence time across all representations? Is that something that sounds?
I'm not aware of any sort of development in that direction. That makes a lot of sense. Actually, so I'm stressing out. I'm stressing the importance of this choice of random functions. But it's quite implicit in the work of Prop and Wilson. Like they basically say there's a very natural random function for that problem they have, and their coupling is using the same random numbers for both. And there is zero discussion of even for the same Markov chain, you could have used another coupling, you could have used another random function. And so I don't think in that literature they explore that question, but you know, it's a good question. Okay, so let me move on to other things that don't provide perfect samples, but they are more applicable, more easily applied to maybe econometrics and statistics at least. Okay. So there's going to be lots of tricks as well, but it's completely different nature of tricks. So let's start with this one, a little applied math trick, probably due to Forsyth and Leibler. And the question is as follows. So you have an infinite series, you sum AKs, and note that maybe it comes from a telescopic representation of a limit, right? Because if you have a limit of interest, so you're interested in a quantity that you can compute recursively, but you're interested in the limit. But the limit can be written as the series of bt minus 1 right? Maybe plus b0. And so that's of the form series of AKs where A0 would be B0, and after that AK would be BK minus BK minus 1. So you're interested in computing this, but you know what you can do is you can stop after t steps and do a large T, hope that it's okay. But the question that they ask is, can you obtain a random answer that is centered in the right place? So an unbiased estimator, a random variable that has expectation equal to that series. And then they introduce a nice trick. Say yes, of course, because any series, in a sense, we could view it as an expectation over integers. So we're going to define an integer, random value. So k takes value 0, 1, up to infinity. Denote by p sub k the probabilities that it takes little k. And then the algorithm is as follows. You draw big K. You compute only up to that time, the element of your series. And what you output is that value divided by pk. Okay, so that random variable, we can compute its expectation. Right, what's random in there? What's random in there is the draw of k. So you sum over all the possibilities. They occur with probability pk, and when they occur, the value that g takes is ak divided by pk. Of course, then the expectation is exactly what you wanted in the first place. This is a nice trick. Not necessarily a good estimate. You may want to see, for example, if the variance is finite. You also want not to wait forever. So, if the time it takes to compute the step k is linear in k, if you can compute basically the a's or the b's recursively, then you do want the expected cost to be finite. So that will impose the pk's to decay at at least at a certain rate. But on the other hand, because the estimates depend on 1 over pk, if pk takes very small values, then g takes very large values. And so the expectation of g square, so in order to try to control the variance of g, you can compute it as ak squared divided by pk and then summed. And that means that pk should not go down too fast, in fact. So when you put things together, you have this kind of trade-off. And in order to have finiteness of cost and variance, at least ak squared must decay faster than k to the power minus 3. Otherwise, you just can't choose any pk that would lead to those properties. So it doesn't work always, and it's not because you have a finite variance that it's a great idea to do that, but certainly it seems like a minimum requirement for an estimator. Yeah, I mean, to be debated. And that imposes the original series to converge fast enough, or the original limit to converge fast enough. And so the question would be, can we do that with MCMC? Yeah? MCMC, there's an average, converges. You can take the limit. We're interested in the limit of the ergodic average. So maybe we can cast this problem into that machinery and do a sort of a randomized MCMC estimator that would have the property of being unbiased. And if you had that, what you could do is generate lots of them on your parallel machines, average. If the variance is finite, you have a CLT as the number of parallel copies goes to infinity. And so you're in good shape. You've basically parallelized MCMC. Yeah. Expectation of K? Because that's probably your cost. The cost of obtaining this estimate. It really depends on the setting, but I'm thinking of in MCMC it would be the case that you need to do the first t steps to get state t plus 1, and so you can't have the cost of obtaining the t steps is linear in t. And I want a finite expected cost. I probably want more than that. I also want probably the variance of the cost to be finite, but at least the expected cost finite. That's sounds like if you don't have that, you may wait for a long time. You could state things much more generally, saying you want to control the moments of the cost and of the estimate. But cost is important here. So.
Is it impossible to sample from all positive integers sample from the natural numbers?
Yeah, like a geometric distribution is supported on the natural numbers. Yeah. Or the Poisson. It's unlikely to go very far, but it depends on the rate, right? There's a good question of if you specify an arbitrary sequence of probabilities, what's the best algorithm to sample from that? That's another question here. Okay, so the next developments come from the contribution first of Peter Glynn and Chang-Han Rui, called exact estimation for Markov chain equilibrium expectations. It's not perfect sampling. They call it exact estimation as opposed to exact sampling. So we're not going to sample from pi, but we'll be able to obtain unbiased estimators of expectations with respect to pi. Okay, and so that's a type of stuff that has been fairly active since then. I'm going to present developments that are mostly explained in those papers and in the review article which I've put on my website, also in the Google Drive, which should appear in the next edition of the Handbook of Markov Chain Monte Carlo. Okay, so the story is as follows. So we're going to start coupled chains. So we're going to run chains 2 by 2. So there's going to be couplings everywhere. But contrarily to the kind of couplings we looked at yesterday, where the second chain, the white chain, was stationary, here there's no stationary chain. Right? We're not allowed stationary chains because we don't know how to sample from pi. So we start 2 chains from pi 0. So here pi 0 bar refers to a coupling of pi 0 and itself. So joint distribution that is such that x0 follows pi 0 and y0 also follows the same pi 0. They could be independent or not, and that's left open. Okay, now we're going to sample the first chain on its own for a little while. So I'm calling L the number of steps that we're going to perform on the first chain. And that stands for lag. It's going to be a lag. A bit like in the telescoping series ID. There's a lag of 1 between BT and BT minus 1. So we're going to do the same type of telescopic stuff. And now, after L steps of X, we have, so we're at step L plus 1. We have XT minus L. So because we haven't changed Y yet, so we have basically, at some point we have XL and Y0. And we're going to sample it jointly from a transition kernel P bar, such that it satisfies the marginal constraints. So again, the 2 chains are going to have the same transition kernel. So the result of that is that XT and YT have the same marginal distribution at all times. So, which is not pi here, which is not the stationary distribution, because neither of those chains start at stationarity. But they will be constructed so that jointly there exists a coalescence time. So we'll call it the meeting time. But it's not the meeting that guarantees that wherever it started, it would arrive there. It's just the meeting between those two chains. Okay? So that's why it's much less stringent as a construction than coupling from the past. We're just going to run two chains until they meet somewhere. So it could look like that's already a fiction. For example, for AR processes, can you run two AR processes so that they coincide exactly in finite time? That's not obvious, right? But it's possible, actually. There's an algorithm that does that. So that's the topic for tomorrow, how to construct those couplings so that, for example, a pair of AR1 process or a pair of Metropolis, Rosenbluth, Taylor, Hastings, a pair of Gibbs samplers, and so on, exactly meet in a finite time, even on a continuous state base. Yeah?
When I imagine chains meeting, I imagine them touching each other at the same time step.
Yeah.
But here, when you wrote xt equal to yt minus.
Yeah, there's this lag. So actually, yeah, maybe the next diagrams will clarify a bit. So this is the trajectory of x and y, and the meeting time is indicated here as tau. And at that time, you don't see anything very clearly, but from that time onward, the x trajectory is equal to the y trajectory with a lag. You can see that there's the same little mountain here and here. But for convenience, it's much clearer if we just shift horizontally the y chain. So if we plot yt minus L instead of yt, then the chains coincide exactly at this meeting time. Okay? So the assumption for today is that we can generate those couplings. And it sounds maybe a bit crazy, but I'm going to try to convince you that if we can, there's a lot of good stuff happening. And tomorrow I'm going to try to convince you that sometimes we can. So I'll go back to the probit example, and I'll describe also a Gibbs sampler for Bayesian quantile regression. Okay. Okay, so what's the point? So in one slide, how you obtain unbiased estimators thanks to those coupled lag chains. So the quantity of interest is an expectation with respect to pi. You can write it as a limit. It's the limit of the expectation of h of xt when t goes to infinity, assuming you constructed your MCMC adequately, so it converges to pi. Okay? A limit you can always write as a telescopic sum. A bit complicated here because I don't start at time 0, I start at time k, arbitrarily. And my lag is of size L instead of 1. Otherwise, it's exactly the same trick as on the board. Okay, so now I introduce steps of size L. I'm going to infinity by steps of size L. And what I have in my sum is the difference between expectation of x at some time and x at some previous time. But I constructed another chain that has the same expectation at all times. So I can replace any expectation with respect to any xt by the same expectation with respect to yt. Okay? Using the identity between the marginal distributions. So now I have an infinite sum of expectations of differences between my test function evaluated at the two chains with a lag. But I've constructed those two chains so that they meet exactly. Right? So I want to say that at some point this difference will be equal to 0 at the meeting time. And onwards as well, because they meet and then they stay together, those chains. Remember the diagram. Okay, so now if I'm allowed to swap the expectation and the limit and the infinite sum, so it's a swap of limit and expectation, it's not always legal to do that, but we'll talk about the conditions later on. If I'm allowed to swap, I have that this is the expectation of an infinite sum of differences. And so that means that within the expectation, I have a random variable. Maybe it's well defined. It's not so clear because of the infinite sum. But that variable has expectation equal to the quantity of interest. Right? We only have equality here. So that variable is an unbiased estimator of the quantity of interest, the expectation with respect to pi. Okay, so just a trick in a sense. And of course, it relies on the ability to construct such couplings. But now, you notice that here, this infinite sum, you would only have to compute it up to the meeting time because the terms afterwards would be all equal to 0. So this infinite sum, in fact, you can maybe compute it in finite time, up to the meeting time. So the capital L it was not actually in the first papers on this. It turns out it's a good idea to do a lag of L instead of 1 in terms of efficiency. And it's also a good idea to not start at time 0 but at time k. But it's not obvious. It makes the notation a bit more clunky, but that's what I'm going to use in practice later. Okay. So here's the algorithm. You choose an integer, k. I'll think of it as a burn-in, so a part of the chain that I'm going to discard initially no matter what. I choose a lag. I can talk about how you choose the lag later, maybe. Sample from a coupling of the initial distribution with itself. So typically, by lack of a better ID, I use an independent coupling. So I initialize x0 and y0 independently from pi 0. Then I do L steps of one chain, and then I do coupled steps until meeting occurs. At this point, I can return. So here I'm writing things a bit differently. I could return the estimate that was before in the expectation. But the test function doesn't matter at all here in the construction. Just a device to say I'm interested in an expectation of h, but the construction here does not involve h. So you can think of it as producing instead a measure, and then you can use any test function you want that you would evaluate at all the atoms in this measure. And so for any h, you evaluate at xk plus jl, and you do that sum, and that's your estimate. And if the previous reasoning works, so if we're allowed to swap expectation and limit, then the expectation of that estimate is equal to the quantity of interest. I think it's funny to look at it from the perspective of a sign measure. We're going to look at pictures maybe in a bit. So where you see that if you only had xk, right, the delta mass at xk, that corresponds to running your MCMC algorithm for k steps. Okay? If k is very large, that's going to be nearly giving you a draw from the target distribution pi. But if k is very small, then it's closer to pi 0, the starting point. And so somehow this sum of differences is the bias correction term. Is changing the distribution of the whole thing so that the expectation is now pi instead of being just pi sub k. So I call this the bias correction term. The bias cancellation term, you could say, because really then there's no more bias. It's funny in the Monte Carlo scene because we don't see a lot of sign measures, so here we have those negative signs here. It's not very desirable, in fact, because it means that your estimate of positive quantities could be negative, could take negative values. Right? For example, if h is an indicator function, you're trying to compute a probability, which is a positive quantity. But here you may have some 0 minus 1 sometimes, and so your total estimate could take negative values, even though it's unbiased. Okay. Any questions so far?
The variance in this case, because you said you should arrange so that to control for the variance, it has to be this.
Yes, absolutely. Yeah, we need to talk about the cost and the variance. Yeah. In fact, that's why we won't use that thing. We're going to make it even more complicated because this would have a terrible sort of variance, basically. In fact, we're going to increase the cost, but drastically reduce the variance. Or you could say that even the reason why we don't choose k equals 0 and l equal 1 is to do completely with the variance, because it's only increasing the cost, but actually it would reduce the variance. Because you're absolutely right, we're not happy with just unbiasedness. We want to know that it's competitive with MCMC. So the kind of results we're going to arrive at is that variants of this are competitive with MCMC in terms of cost and variance. But they're unbiased, so they're much sort of immediate to parallelize. That's going to be the line of argument, which I'm happy to be contradicted on, of course. Okay, so quick thing is that it turns out you can rederive exactly the same estimator in another way. So we were not trying to do that. We were trying to derive a new estimator, and it turns out that we ended up with the same estimator. But it's still interesting because it relates to the so-called Poisson equation, which we've seen yesterday. Probably I'll finish on that today, and I'll finish those slides tomorrow. So remember the Poisson equation, which was introduced for the purpose of obtaining a CLT. And it's, you give yourself a transition kernel P, a test function H, and you're looking for a solution of this equation that is a function G satisfying this. So if you rearrange a bit, you put pi of H on the left, and this is a function, so here of Y, for example. So if you look at it this way, you have this thing which is not a function, which is a constant, that's equal to this for any Y. So in other words, on the right-hand side, you have a constant function. Okay? But you know how to evaluate the first term, H of Y, that's easy. You plug any Y, you know how to evaluate H of Y. Now, in order to ultimately estimate pi of H, maybe you can try to think about whether it's possible to estimate PG minus G of Y. Maybe it's going to be somewhat easier. So let's see. How do we estimate PG minus G? So we looked yesterday at one of the fishy functions, the solutions of the Poisson equation. G star maps X to this infinite series of conditional expectation after T step of the centered function. That doesn't look super nice to estimate from the onset, right? There's an infinite sum. There's pi of H, which we don't know. I mean, the whole point is to estimate pi of H. But if you recall, if this is a solution, we can add any constant to it and still obtain a solution because G minus PG is invariant by additive constant. And so in particular, we can subtract G star of Y. Okay? So new function now called G sub Y that maps X to G star of X minus G star of Y. And now, at least, pi of H disappears. We can write the difference between the two series as the series of the difference here between PTH of X and PTH of Y. Okay? I'm assuming here everything is well defined. All the series are finite. Okay? And now, okay, so now let's think. PTH of X is the conditional expectation of H of XT given that the chain started at little x. PTH of Y, same thing for a chain that starts at little y. So from this, you kind of want already to start two chains, one at x, one at y. Evolve them according to the Markov kernel P marginally, but in such a way that if they could meet at some point, maybe you can approximate this infinite sum by a finite sum. Okay? So that leads to following estimator. So big G sub y of x is obtained by exactly this construction. There's no lag here. There's no lag in that story. There's a chain starting from little x and a chain starting from little y. They meet at some point, which we call tau again. We can compute the difference between the two chains up to that time. After that time, of course, the difference is 0. So I could have written this series as an infinite series. And then it's a question of whether the expectation of this is the series of expectations, which is little g. Again, it's a question of whether I'm allowed to swap an infinite sum and an expectation. So we need some conditions for that to happen. But if the conditions hold, then we know how to estimate little g. So we're nearly there. We didn't want to estimate little g. We wanted to estimate pg minus g. Okay, but it's nearly the same. That's where the lag comes in. You fix an arbitrary little y. You do one step of MCMC. Okay, so you get big X. And now you compute the previous estimator, meaning you're starting a chain from big X and another chain from little y. The same little y than before. And now you compute the expectation. So we just said that this could be distributed, have expectation equal to that. So here we're conditioning on X first. We're integrating the randomness in the couple chains. G sub Y is G star minus G star of little y, which is just a constant. And of course, what is the expectation of G star of big X if we started from little y? It's just P G star of little y. So here's a way of estimating pi of h. You do one step of MCMC from any arbitrary little y. You evaluate the test function there. Then you do your two chains, one started at big X and one from little y until they meet. Compute this thing, and this sum is an unbiased estimator of pi of h. Okay? And it turns out it's exactly the same as Glynn and Reed. So we were disappointed. We thought we had a great new ID, and it's exactly the same ID. But here, there's no little k and big L. So you can, in fact, generalize this. If you want a lag of L, you do the same story with the Poisson equation for the iterated kernel P to the L. And instead of starting from a fixed little y, you can start from a distribution. Randomize the starting point. And if you randomize the starting point to be P sub k, you're exactly back in the same scenario as before. Okay. So maybe I'll finish with just a diagram. So you have a target distribution, and you're trying to approximate it. And I'm going to take a very cartoonish example of bias. Suppose that your MCMC only gives you this. Okay, so this was the target. It has 3 modes. But suppose I'm starting my MCMC on the left, very far away from the center, and I'm not doing enough steps. So I have a big bias that I can see easily on my graph. Okay, so I get this. So I have visited all the modes, but not in the right proportions at this point. So if I compute the bias correction term for this particular example, this corresponds to a toy, a Gibbs sampler. And I can decompose my bias correction term so you can see the positive part, the part that is associated with a positive weight, and the part associated with a negative weight. And you see it's doing exactly what you want. So you had too many points on the left, not enough points on the right. And when you compute this, the positive part of the bias correction, puts mass on the right and removes mass from the left. So in a sense, it feels like you need that kind of sign measure construction because you need to remove some mass from where the chain has been too many times compared to the target. Okay, I'll stop here. Thank you.